All right, let's go ahead and talk about functions. All right, so what are functions? Okay, so if we want to talk about functions, we probably should talk about the different parts of a function, right? So first off, we define a function as each domain has exactly one range. And, for that, you would have to also know what domain and range means. Well, domains and range, it's pretty simple for us to define. Domain, pretty much we can just say it's every value of x that is being used. And range is every value of y. That is being used. Now, let's go ahead and dig into what a function looks like, right? So let's say I wanted to, graph the linear graph here. Let's say I want to do y equals to 2x plus 3, right? I want to graph that. So how would I go about graphing that? Well, first off, I need to know what is the slope and the y-intercept. And the slope is always that coefficient in front of x. And the y-intercept is always the number being added or subtracted to x. And I'm going to use those two pieces of information to help me graph it. So I'm going to draw my graph now. And then this is my origin 0. And I'm going to first graph my y-intercept, which is positive 3. So this is 0. And then I'm going to go 1, 2, 3. And I'll go ahead and put a point right there. And now my slope is 2, right? So remember that slope is rise over run. So it's actually 2 over 1, meaning from every point I'm going to go up to right 1. So from here I go up to 1, 2, and then over 1. And so my second point is right there. And then I go and connect these two dots to draw my graph. So that would be y is equal to 2x plus 3. Now, let's compare that to something where if it were written in function notation. So, what would it look like with function notation? It would look like this. F of x is equal to 2x plus 3. Now, let's say I want to graph this, right? How would it be different than what I just did? Well, the answer is it's not different. It's actually the exact same thing. This is right here would actually just be y equals 2x plus 3. So if you want to graph this, you would just use the graph that we did back here. Now, I know what some of you might be thinking. You're probably thinking, well, what's the point of that? Why do we write f of x, right? I mean, why can't we just write y? Why do we have to always complicate math? And I'm kind of with you at that. Why are we always complicating math by adding stuff that seems pointless? But, I gotta tell you this though. It's not really pointless, all right? Because why? Let's remember what the definition is, right? A function, each domain has exactly one range. That's what a function is, right? That means that whatever I put in, I have to get exactly one thing out, right? Like, for instance, let's say my function were this like magic box right here, right? Okay, so this is my function. Okay, and whatever goes inside, I can only get one thing that comes out, right? For instance, let's say I throw in a strawberry, right? So this is my strawberry right here, and I put it into a function, and out comes my strawberry milkshake. Okay? See, this is my strawberry milkshake. Look at that. You know, it's got boba in it too. Because, you know, you kids like boba, I think, right? See, so that's what a function is. You put one thing in, you get one thing out, right? And let's say instead of a function, right, we had something called a relation. And a relation is different from a function because with relations, let's say I put that same strawberry in, right? Do this. I put it in. And instead, I come out with 2 milkshakes. But they're not both strawberry. Instead, I get 1 strawberry. Oh, that's a weird looking cup. Whatever. Anyways, and 1 chocolate. Okay? So that's the difference between a function and a relation. Function, 1 thing in, 1 thing out. Relation, 1 thing in, 2 things out. Well, I should probably put an arrow right there, huh? So that's why it's important that we know what a function is. A function tells us that when we put 1 input in, we get 1 output. So that is why we use f of x. And you know, when you guys are going to take your SATs and learn more difficult math, you'll see some really crazy stuff. Let me give you an example of that. So let's say it had f of x equals to, you know, let's come up with like negative 2x minus 5, right? And then you saw something like this. G of f of 3 equals to 5x minus 1. Have I just completely lost you at this point? Does this look totally hard? Like something that you're just like, whoa, what the heck? How am I supposed to solve this? Well, it's not hard. It's not hard. It's actually really simple, okay? So this tells us that the f of x, or the function of f, is negative 2x minus 5, right? And then g right here, yeah, it's a totally different letter. But really it's just saying this is a second function, all right? We're looking at 2 different functions. And whatever we plug in for x here, right, will give us an output, 1 output, right? Whatever output we get from that, we use it for this function. So how would I do this? And now, you know what? This is a little bit advanced, I'll bet, yeah. But what I'm trying to show you is that it's not impossible. It's actually quite doable. It's something that you can actually learn how to do now, not 2 years from now, 3 years from now. This is, you know, it's all the same stuff. So let's say I want to solve this, right? So I'm going to find out what the function of 3 is and use it for the g function, right? So let's go ahead and do that. So let's say I want to plug in 3. So f of 3 equals to negative 2. Now remember, we're not using x now, we're using 3 times 3 minus 5. Well, what does that give us? Well, we go and work it out. Negative 2 times 3, that's negative 6 minus 5. Okay? And then we go ahead and combine those two, and what do we get? Negative 11. So f of 3 is equal to negative 11. Now notice what I just said, f of 3. That's how we kind of describe functional notation, right? Whenever we have a value in place of x, you know, because this is called f of x, this is called g of f of 3. That's how we describe it in words, if we were to like say it to someone. So f of 3 is equal to negative 11. Now I'm going to go ahead and use that for this function. So instead of f of 3, which is equal to negative 11, I'm going to go ahead and put g of negative 11 is equal to 5 times negative 11 minus 1. All right, what does that give us? Well, negative 5 times negative 11 is negative 55 minus 1. And then we go ahead and work that out. And what do we get? Negative 56. And that's how this whole notation works. That's how functions work, right? That's why we learn this stuff. So let's see, you know, stuff that you know, let's try to get into stuff that's more like real world, right? So, first of all, you should know that there are a lot of different functions, right? We have linear functions, right? Which, if you look at a linear function, it's a straight line, like this. That's what we call a linear function, right? And then we have other things called exponential functions. And typically they look like this. Well, you know, I could do it like this too, right? Because that's technically exponential function. Now, when do we ever see an exponential function? Well, you're in luck. I don't know, wait, I shouldn't say in luck. You're living at a time where exponential functions are relevant. Okay, so let's say I want to create a function, right? Let's say I'm given a table. So let's start with this one here. So let's say I need to write a function for this table. I need to write a function that will help me predict what I would get if x were equal to 20, x equal to 30, without having to actually count all the way through, right? You know, so I'm going to show you different methods doing this. All right. So one method is this: you have to figure out, well, what relationship does x and y have? How do you get 10 from 0? So we look at that and we think to ourselves, well, you could multiply 0 by nothing, because, you know, 0 times anything is 0. You could add 10 to 0. That would give you 10. So maybe it's x plus 10 equals y. Right? That's a function that we could test. And then we want to test it. Would that work with all the numbers that we have here? So 0 plus 10, yeah, that equals 10. How about 1? Does 1 plus 10 equal 12? Well, no, that gives you 11. Oh, okay. So that doesn't work. Now we have to like really put on our thinking caps here and figure out, well, am I missing a step here? You know, like 0 plus 10, okay, and then 12, huh? And then you think to yourself, well, what if it's like x plus 10 plus 2? Would that work? Right? You know, we're doing this like guessing check method here. You know, and I'm going to show you in a little bit a much quicker way of doing this. But I feel like let's start at the very, you know, basic level here in order, and then work our way up to something more advanced, you know, because I can show you the more advanced way. But if you don't know all the steps that lead up to it, what would be the point of that? I'd be wasting my time and yours. So let's just, you know, start at the very bottom and work our way up to the top. So let's say, you know, we had this. Would that work? Well, you know, x plus 10 plus 2, that's just 12, right? So does that give us our answer? Well, you know, 1 plus 12, that equals 13, so that doesn't work either. Is it 11? Well, yeah, maybe we can try that. Does 1 plus 11 equal 12? It does, right? But what about 2? Does 2 plus 11 equal 14? No, it does not. That equals to what? 13. So now at this point, some of you guys be really frustrated, like, oh man, what's going on here? You know, like I'm adding these numbers, it works for some, it doesn't work for the rest. Man, math is really hard. You know, what do I do? Now, here's the thing. You have a toolbox, right? You've got your little toolbox here. And in your toolbox, you've got a lot of different tools. Your tools are addition, all right, subtraction, multiplication, and division. You've got tools. You've got a lot more tools than this, obviously, as you know, you learn more math. But these are your most basic tools that you've, you know, gained through your, you know, education from kindergarten to now. And we can use these tools to help us create this function. Now, remember in all these other functions that we looked at, it was never just one operation, right? Like you had multiplication going on here. So maybe we can use multiplication to help us with this one here. Now, I noticed this. 2, 4, 6, 8, 10, right? These are all the numbers that are being added to 10. So what it looks like to me is that you have an x, and then you have plus 10. But here's the thing though. When x is 1 and you add 10, you only get 11. When x is 2 and you add 10, you only get 12. So maybe we can multiply x by a number to help us with that. And what number do you think that would be? How about we try 2? Would 2 work? Right? So let's test that out. 2x plus 10, does that work? So let's see here. If I plug in 1, right, I get 2 times 1 plus 10. That gives me 2 plus 10. That equals 12. Yeah, that works. How about 2? I get 2 times 2 plus 10. That becomes 4 plus 10. That equals to 14. That works. How about the next one? How about 3? 2 times 3 plus 10. That gives me 6 plus 10. That equals 16. That works. So it'll work. It's worked for 3 numbers. Well, 4 numbers if you count 0. It's probably going to work for all the numbers, right? I've already tested enough. So what if I want to find, if I were to continue this table and I want to find the value of 500 without having to write the whole table, could I do it? Yeah. All I do is this. 2 times 500 plus 10. Well, this is 1,000. Plus 10, that gives me 1,010. That would be the number. See? So then that's the whole point of functions, right? We use these functions to help us do something called predictions. You know, because predictions are very helpful in helping us figure out, what do we know about the future? What can we guess about the future? And this is what we use to help us make these decisions. You know, do we have enough things for the future? Do we have enough money? Do we have enough respirators? Do we have enough doctors? You know, stuff like that, right? So my function for this case would be f of x is equal to 2x plus 10. So we've done that with a table. We can also do it with a graph and a mapping diagram. For example, let's say I want to find the function of a graph that did this, right? Where, let's see, I go 1, 2, 3, 4. Let's say I want to find the function of this graph here. How would I do it? Well, you already know how to graph that. You needed what? 2 pieces of information, right? Remember we talked about that? You need to know the y-intercept and the slope. So where's the y-intercept? Well, it's simple. It's right there. Remember y-intercepts? That is exactly where the graph crosses the y-axis. This is y, this is x. So our y-intercept is, let's see here, 1, 2, 3, 4. Our y-intercept equals 4. So I'm going to go ahead and put b equals 4. Now, okay, a lot of you guys already know why I use b. Some of you guys might have forgotten. You know, we'll get into that in a second. Next thing you need to know is the slope. And now remember that the slope, right, is rise over run from point to point. So from this point to this point, I'm going down 1, 2, 3, 4. So it's -4. So again, from here to here, I'm going down 1, 2, 3, 4. We always go from left to right. Okay, never right to left. All right, and then the run is 1, 2, 3, 4. Now, -4 over 4. I can simplify that. That's going to give me what? -4 divided by 4 is -1. So, I'm going to go ahead and put m here. All right? Again, yes, I've used another letter, right? But m and b have very specific definitions. M represents slope. B represents y-intercept, and we use that in the slope-intercept form, y equals to mx plus b. So b equals 4, m equals -1, y is equal to -1x plus 4. Or f of x equals to -1x plus 4. And that would be the function for this graph. And that's how we find the function for graphs. You find your slope, your y-intercept, and you're done. All right, let's take a look at mapping diagrams now. So mapping diagram is a lot like a table, only we have arrows involved, okay? So let's say for this mapping diagram, I use -2, -1, and 3, okay? And then for y value, well, you know what, since I'm kind of like just doing this on the fly, I have to make sure that this is gonna make sense. Okay, all right. Okay, I got it, all right. So we're gonna go at 0, right? 1 and 5. So what the arrows represent tells us that when I plug in -2, I get 0. Plug in -1, I get 1. Plug in 3, I get 5. Sure. Now, what kind of function could we come up with this? I kind of made it kind of easy. All right. Let's think about this. What can I do to -2 to get 0? Well, for a lot of you guys, I'm sure the answer came really quickly. But some of you guys may have trouble with negative numbers, right? So remember, whenever you're having trouble with negative numbers, draw yourself a number line, right? So in the middle you have 0, and then over here you got 1, 2, 3, right? Right side is positive, left side is -1, -2, -3. All right. So what do I do to get from -2 to 0? Well, I go right twice, which is also the same thing as adding 2. What do I do to -1 to get 1? I go right twice, which is the same thing as adding 2. What do I do to 3 to get 5? I go right twice, which is the same thing as adding 2. If I were to go left twice, what do you think that would be? It'd be subtraction, that's right. But since I'm going from left to right, it's addition. So as you see here, whatever we do to x, we add 2 to get y. X, add 2 to get y, x, add 2 to get y. So y is equal to x plus 2. And we could write that as f of x equals to x plus 2. All right, so we've done tables, graphs, mapping diagrams, right? And we've talked about domain and range. Now, let's talk about independent variable and dependent variable. All right, so when we're talking about independent variable and dependent variable, what we're talking about is this. Which of the two things is affected by the other? Let's come up with an example, right? Let's say Mr. Hassan gets paid $5 an hour, okay, for every chore he does. All right. Now, first off, what are our variables? Well, he gets paid $5 an hour for every chore he does. So the independent variable would be how many hours he works. What would be the dependent variable? How much money he makes. Now, notice something about variables, right? Whenever we talk about variables, we're always talking about a quantity, right? Something that we can count. Independent variable is how many hours. Dependent variable is how much money he makes. It's always something you can count. It's never something like, chores or my son, right? It's something that we can count. And the reason why this is important is because we need to know what's affected, what's unaffected. right? So for example, hours. Time will continue and it's unaffected by what my son does. But the amount of money he makes depends on how many hours he works. See? And the way we think of it is this. Your independent variable is always going to be your x-axis every single time. And your dependent variable is always going to be on your y-axis. And you see that when we do tables, graphs, and mapping diagrams, right? So for 0 hours, my son makes $0. All right. And I'm going to do this as 5, 10, 15, 20, just to make it easier on myself, right? First hour, $5. Second hour, $10. Third hour, $15, and so forth. And you see that this creates a graph. Now, the graph starts at the origin. I'm not going to continue the graph this way. Why? Because that doesn't make a lot of sense, right? Like, I can't, that would mean what? Like, if it were negative hours, which I'm not really sure how that would even be possible without a time machine, that would mean if I could reverse time an hour, he'd have to pay me $5, which would be amazing. But I can't do that, right? Because I can't reverse time. So that's why your graph just continues here in the first quadrant. So that's how we figure out what independent variable and dependent variable are. And again, simplest way to think of it, independent variable is your x-axis. Dependent variable is your y-axis. Okay, let's talk about exponential functions. And how they can be very important to know how to do. So let's say, hypothetically, there is a person, okay? And this person, ate something weird or got bitten by some strange animal or got hit with like a alien meteorite, I don't know. But they got sick. They got sick and they have a virus, okay? And they don't know that they're sick, but what they have is very contagious, meaning a lot of people can catch it just by being around them because it's airborne. So this person shows no symptoms, and symptoms are like, coughing, sneezing, throwing up, things like that for 5 days. And so for those 5 days, that person travels the world, right? Because maybe they have a lot of money, takes the subway every day, or a bus, likes to go to the gym or to the beach or anywhere where there's a lot of people. And this person goes to these places, for those 5 days, right? So they do these things. And we can make a table showing how many people are infected with this virus, right? So I'll go ahead and put X and Y right here. And remember, X is our independent variable, Y is our dependent variable. X, in this case, is going to represent how many days have passed. And Y will represent how many people are infected. So, day 0, right, you have patient 0. That's what we call the very first patient or the person to get the disease. All right, so let's say they do all these activities and, they break, they don't really do that social distancing. And on day 1, they've infected 8 other people. So now on day 1, 9 people have the virus. And again, it takes 5 days to figure out whether or not you have symptoms. So day 2, well, let's think about that, right? 1, 9, next number would be 17. But is it? Right? Didn't we say the first person will infect 8 people? Right? So now you have 9 people who will go on to infect 8 people. Right? Because, let's say all these people are going around and they're doing all the same fun stuff that the first person did. So in that case, if you have 9 people who each can infect 8 people, day 2 would be 72 people. Okay? And then day 3, 72 people go on and they go ahead and infect 8 other people. So how many people would that be? Well, we have 72, multiply that by 8, and what do we get? 576 people. How about day 4? Okay, multiply that by 8. You get 4,608 people. And then day 5, 36,864. And as you can see here, this is pretty dramatic. Right? To go from one person, day 0, and 5 days infecting 36,864. You know, and most people would be like, whoa, wait a minute. That's crazy. You know, like, could that many people in that few days really be infected? Well, you know, I'm trying to describe a disease that is just extremely contagious, extremely infectious, and you've got this first person who's just traveling, going on planes, breathing the same air as other people for about, 8 hours, 10 hours. You know, how many people would normally, on average, be on a plane like that, right? You know, I'd say around, 100, 200 passengers, right? And then let's say some of these people, like the stewardess or the, air marshal, they continuously fly on these planes, and if they're infected, they would pass it on. So, there are a lot of factors involved whether or not this is feasible. But I think with today's day and age, and the situation that we're currently in, we can all really see that this could be a strong possibility. So let's say we try to graph something like this, and I'm going to try my best here because the numbers have gotten really large really fast. So when we try to graph it, we're only going to use the first quadrant, right? And the reason why we use the first quadrant is because it wouldn't make sense to have negative days, or negative people for that matter, right? And we have to understand that there's 2 types of graphs we can use here. We can use something that's called a continuous graph, right? Continuous graph, or a discrete graph. Now, what would be the difference between these 2 graphs? Well, continuous graphs are when you have these graphs where you have this connected, nice looking line, right? And in this kind of situation, this would be best used when values can be decimals, can be a fraction or a decimal. And what about a discrete graph? What would that look like? Well, it would look like this. You'd have a series of dots. And the reason why you would have a series of dots is because the values can only be represented as whole numbers. For example, let's say I'm running a daycare and X represents number of days that go by, and Y would represent number of babies in my daycare. Now, if I were to connect all these dots, that would be me saying that I could have half a baby, and that's not really good to have, right? So that's when we use discrete, right? So this is best used when values have to be whole numbers. So in this type of graph, what type would we best use, right? So again, remember X represents number of days, and Y represented number of people infected. And like I said, can't really have quarter or half a person. So let's use a discrete graph. So at 0, we had, and let me use this here. Let's do this by tens. I know that's not going to really help me once I hit 3 or 4, but just showing you what it looks like, right? Okay. So at 0 we had 1, right? That's our first point right there. At 1 we had 9. At 2 we had 72. And at 3, we had 576, which is way up here. So just going to connect it just to show you what it would look like. And that would be the graph, more or less, if I were to connect and show you a nice continuous graph connecting the dots. And this is what we call an exponential function, where you have this really quick, rapid growth. Now, let's try to understand what would happen if we were to compare this to the number of hospital beds that are available to patients who get infected with the virus, right? So let's make a new graph here. So let's say this graph represents the number of infections, right? And let's say we want to set it up against a graph showing the number of available hospital beds for people who are infected with this virus. So let's just say it goes like this. Now, at this point here, this is where you would expect the number of patients and the number of hospital beds to even out, meaning that however many people are infected have a spot in whatever hospital they go to. This is the point where things get scary. This is when the hospitals become completely maxed out and they say, you know, we can't take you in here. We don't have any room to put you. And that's when these pandemics can get extremely frightening, because now doctors, they have to make this decision of who gets to come in and get treatment and who doesn't, right? And this is the point where we need to use social distancing, quarantines, and all these different types of strategies to help level off the spread of the disease. Now, clearly we would like to eradicate the disease, but that takes time. What we have to do is to make sure that these diseases don't overwhelm our health system, our healthcare system, so that we can treat the people who are infected as well as try to contain the virus. And as you can see, this exponential function is extremely useful for the events that are occurring today. And that's why it's really important that we understand and know how to use these functions. All right. Well, hope you enjoyed this lesson. I know I did. And I will be happy to see you guys for the next one.